Now we'll come to some numerical problems here. So a very small quantity of liquid having a surface tension is given here. So in between two plates, there is a liquid. And this liquid is forming a circular spot, a circular liquid. Two glass plates in between a circular spot, they are making liquid. So the liquid is in this way. In between there is a liquid. And it's a circular spot. See it in circular with the diameter d. Diameter is the d. So here the surface tension force is acting, pressure force is acting. So here the pressure is Pi, let you take, here the pressure is Pa. Here pressure is Pi, here pressure is outside pressure. Now, from the concept wise, this Pa should be greater than the Pi. That's why it is holding the two plates, according to this. But we are thinking about the delta P, the difference pressure, differential pressure, how much here. So this pressure is acting in this area, this circular portion area. So force due to the pressure difference here should be equal to the force due to the surface tension. So force due to pressure difference. So force due to the pressure difference, it is acting over this peripheral area. So force due to the pressure difference, this pressure difference into area. Which area? This area, we can write it down. Pi d. Pi d is the circumference into the height. H given small distance. The two plates separation. So that is only the pressure is acting over the circumferential area. The pressure is acting. This pressure will be equal by force due to the surface tension. So force due to surface tension. So force due to surface tension is acting here. So force due to the surface tension will be either this side, otherwise this side, surface tension. Sigma into pi d, the top side, and bottom side again sigma into pi d, so sigma into 2 pi d. These two forces. So either because surface tension, liquid and solid surface. At the top, there is a layer, interface. Similarly, bottom and the liquid. Bottom plate and liquid. So two possible places there is a interface is there. So these two forces will be equal. So delta P pi dh equal to the sigma. That is the scenario of this equilibrium. So delta P sigma, we are getting it. Now they are asking it, what is the force required to pull the plate? Because there is a vacuum, so equilibrium condition. What is the force? Enough force is required to pull the plate. So outside, also the same, P atmospheric. Here also the pressure difference PA minus Pi, same delta P. So the force required to pull the plate is equal to, so you have to overcome the pressure difference. Pressure difference into the area. So you have to overcome pressure difference into cross-sectional area. That is nothing but pi by 4 d square. Pi by 4 d square. because you want to separate the plate. Now the PI is acting on the surface and PA is acting in this way because of this surface. So pi d square, the surplus part. That's why pi by 4 d square is coming. So delta P is already 2 sigma by h pi by 4. So hence you are getting it. Pi sigma d square by 2h. That much force you have to give to pull the plate. That is one problem. We'll go to the next problem. It is easy problem. Force due to the surface force is equal to force due to the pressure difference. After making it, they are in equilibrium condition and inside pressure is small. Now you want to separate this thing. So you have to overcome the pressure difference, force due to the pressure difference. That is the concept in here. Because PI giving force at here, similarly, the PI is also, there is some force from here also. So you have to overcome this force. Pressure is acting throughout there. Next question is, if the surface tension water air interface is given, already sigma value is given to you, 0.073 Newton per meter. The gauge pressure inside a raindrop. Gauge pressure means what is the pressure above atmosphere or the raindrop. So raindrop is it's a water drop inside fully water. If you remember the formula, you don't remember all the formula, just remember a single formula. Delta P is equal to 1 by R1 plus 1 by R. That is enough to remember. Now, as it is spherical in nature, R1 is equal to R2 is equal to R. So, 2 sigma by R. In terms of the diameter, 4 sigma by D. Okay. That is nothing but the pressure difference. Inside pressure, outside pressure. Outside already atmospheric pressure is there. So delta P is always it is coming is in terms of gauge pressure. It will come in terms of the gauge pressure, always. Because delta P is Pi minus Pa. So Pi is atmospheric pressure. So above atmospheric, what is the pressure? That is nothing but delta P. So you are asked to finding out the delta P. This question. So sigma is given, D is given to you. 0.073. D is given 1 into 10 to the power minus 1 millimeter. So you convert it into the meter. So 73 into 4. 92. So your answer is a D. So you need not to think about it. You just remember this formula. All problems, this kind of the problem can be solved without saying anything. It is a quite interesting problem. Just concept I am giving. Calculation will be the trial and error. It is this kind of the problem. So one spherical here, one spherical bubble and another spherical bubble coalesces, and they will make another bubble. So this one bubble and another bubble, this soap bubble, this diameter is here, Di is equal to T1 is equal to 20 mm. One 20 mm bubble, another 40 mm bubble coalesces, and they create another bubbles. So what is the diameter of the bubble? You are asked. If the process is isothermal process, we are considering atmospheric temperature is not changing. T is constant. Our consideration atmospheric temperature is not changing. In such a situation, what would be the consequence? So you see it is a good question. So the spherical bubble, if you remember again, for case of the bubble, sigma delta P You remember the same formula, nothing else. 1 by sigma. As it is the bubble, so bubble inside air, also outside air. So this thing will become twice sigma into what it is spherical. So 1 by r plus 1 by r. So 4 sigma by r. You can write it down, or 8 sigma by E. You can write it. Delta P. Why here twice? Because two interface. Liquid air, outside air, liquid inside air. So that's why it becomes twice. And R1, R2 and is equal to R. Because it is a spherical in nature, so everywhere curvature is the same, and this is the radius of the sphere. So this delta P is equal to 85. So delta P is nothing but P internal is equal to P atmospheric is equal to 8 sigma by. So Pi is equal to atmospheric pressure by 8 sigma by. This case of the bubble. We'll consider. Now if you consider the first bubble. So first bubble number 1. What is the pressure inside? P1 is equal to Pa atmospheric pressure plus 8 sigma by. Second bubble. P2 Pa plus 8 sigma by D. Third bubble. P3 Pa plus 8 sigma. Pressure is like that. Now inside there is a air is only there. Mass of this bubble here is the M1, is the M2, is the M3. So from the mass conservation principle, you know M1 and M2, because first and second coalesces and form the third one. So M1 plus M2 is equal to. Every bubbles having the air, so we are just multiplying both sides RT. R is the universal constant. R is the gas constant. So this M1RT plus M2RT is equal to M3RT, which is sufficiently gives you the equation. Side thermodynamics will be here. P1 V1 is equal to P2 V2. P1 V1 plus P2 V2 is equal to P3 V3. The isothermal cases. So your equation came P1 V1 plus P2 V2 from mass conservation is coming. P1 atmospheric plus 8 sigma by D1. V1, the volume of the sphere, 4 by 3 pi D1. P2, Pa plus 8 sigma by D. P2, 4 by 3. P3, Pa plus 8 sigma by D3. 4 by 3. On both sides, 4 by 3 pi will be cancelled out. And this will be the remaining. This is the only equation where Pa is given to you. Pa is given to you. That's the given values. D1 is given. You know D1, D2, sigma. All the values you are given. So only you have to finding out D3 values. You have to finding out the D3. It's the only unknowns. But here the cubic equation will come, so it will be difficult to solve. Such a cases you will. So here the left hand side full known. Pa is given, sigma is given, D1 is given. Similarly, D2 is given. So everything is given. The left hand side full known, right hand side is unknown. So right hand side unknown is the D3. It will comes in the cubic form, D3 cubes in form. So if you go for the trial and error, there are 4 options given. If you go for the trial and error, you will see the answer is coming. It's nearly 41.6. By putting the values, you can check this. But conceptually, I'm telling this question is taken because from the it's the sense of thermodynamics is given, isothermal in nature, and continuity equation will be here because same amount of the air is there. So mass of the air in the first bubble plus mass of the air in the second bubble would be equal to the mass of the air in the third bubble as the bubble coalesces. That is the concept here. And the last problem, we are going to solve the capillary effect problem just to solve this thing. Capillary effect problem, if you remember the formula, otherwise if you not remember, that is also not a big problem. You can derive it within 5 minutes. It will take only 1 minute to derive. Just what concept you will take and derive it. It will take very less time. To the surface is the capillary height. At the height is H. So there's a sigma. So what is the upward force? Sigma pi d. D is the tube diameter and cos theta, the upward force. Upward force is holding the weight of the liquid, extra weight of the liquid. That is the weight rho g into volume. What is the volume? Volume is the pi by 4 v square into h. So what is the h is coming here? 4 sigma cos theta by e within 30 seconds it is done. Then you were asked to finding out the water. First, in the case of the water, you take it as a pure water, so sigma you can take it 0. Pure water and glass tube. So contact angle is 0. So here nothing else is just you put the formula, everything is given to you. 0.073575 into cos 0 is 1, and diameter of the glass is given 4 into 10 to the minus 3 into density of the water is given 978 at 20 degrees centigrade into G. So it will gives you the value. It will be around 7.6. Check this millimeter in terms of the same way for the mercury. Sigma is contact angle is given 130 degree. So here, if you put it 4 into 0.51, that is the sigma of Hg, cos 130 divided by 4 into 10 to the minus 3. Now the density of the mercury is actually 13.6 is the specific gravity of the mercury. So 13.6 into 20 degrees centigrade water density is the 978 or 1000. Better to write it 1000 because it's respective to some 1000. So 13600 into 9.8. So it will come also around 2.5. We'll check the calculation. Just the concept is here, direct formula basis this problem, nothing else here. So here we conclude the surface tension. The surface tension, the main thing is the formula of this previous formula of whatever we are seeing. Goes on. The curved surface is the main thing where we can getting it in this way. So here we finish the surface tension. So the properties of the fluid is almost covered. Only the remaining is the vapor pressure. Vapor pressure concept, we'll tell it later. So up to this, the property of the fluid is complete here. Next topic, we'll start the module 2 of the fluid statics topic.